Hello everybody, this is Alex Voss, your professor at TVE course. And this is our expanded class on transformers. A transformer, as we talked about earlier, is an electrical device that takes electricity of one voltage and changes it to electricity of another voltage. Of course, this has to be AC voltage. There's no such thing as a DC transformer. Even though what we often do is we can take DC, convert it to AC, and then feed it to a transformer, and then take it back to DC, thereby converting one voltage of DC to another voltage of DC. But a transformer has to be an AC device, and it consists of two windings, an input winding or an output winding. And depending on the number of turns in a winding, if we have less turns on our primary input and we have more turns on our secondary of the transformer, then it's considered a step-up transformer because it will take a lower voltage and make it a higher voltage. If we have more windings on the primary and less windings on the secondary, then it's a step-down transformer. That means we'll be taking the voltage coming in and stepping it down. Now, as always in transformers, even though there are several types of losses, the power is a continuous thing. The current will be dropped when the voltage is increased, or vice versa, to keep the power the same. And there is some loss in the transformer, so it's not totally efficient. So basically, it's not a power increaser, but a voltage increaser or decreaser. And basically, there's a formula, Vs over Vp equals Ns over Np, where it's the voltage on the secondary over the voltage on the primary is equivalent to the number of turns on the secondary over the number of turns on the primary. Now, here is a public domain film produced by the U.S. Air Force, which does an excellent job of expanding and explaining how transformers work.
Now, just what is a transformer? Well, basically, we can say it's a device that does just what its name implies. It changes or transforms voltage. If the transformer reduces the voltage, as in the case of the train, it's called a step-down transformer. Whereas if the transformer increases the voltage, as in the case of the fluorescent light, it's called a step-up transformer. The ability of the transformer to transform voltage can be understood best if we first examine an important phenomenon in electricity, the magnetic field. When electric current passes through a wire, an invisible band of magnetic force is set up around the wire. In the case of direct current, this magnetic field expands to a certain point and stays there, except, of course, it's traveling around the wire all the time. For instance, if you were to grasp the wire in your left hand and extend your thumb in the direction the current is traveling, the magnetic field will be circling the wire in the direction of your fingers. In alternating current, the magnetic field expands and contracts every time the current changes direction. And now here comes the payoff. This phenomenon gives a wire carrying alternating current the power to induce a voltage in a second wire placed beside it. How come? Well, the second wire will pick up voltage from the wire carrying the current because the magnetic field expanding and contracting through the second wire induces this new voltage. This is called electromagnetic induction, and it's the principle on which the transformer works. Remember, a magnetic field surrounds every live wire. Now, in order to concentrate the strength of this magnetic field, we coil the wire, thereby intensifying the magnetic attraction inside the coil many times over. The coil that carries the current is called the primary coil. Beside it, we place an additional coil called the secondary coil. Notice that the magnetic field from the primary coil travels across the gap to the secondary coil. So we can increase the strength of this magnetic field even further if we place an iron core inside the two coils. Now all the magnetic field will travel inside the iron core because it offers less reluctance than the air around it. Now this in turn permits a greater amount of energy to be transferred from the primary to the secondary coil. This process of transferring electrical energy, or voltage we might say, from the primary coil to the secondary coil through electromagnetic induction is commonly referred to as transformer action. As we said before, the transformer can step a voltage up or it can step it down. The voltage increase or decrease is determined by the turns ratio of the particular transformer. The turns ratio is the ratio of the number of turns in the primary coil to the number of turns in the secondary coil. For example, if the primary coil has 500 turns and the secondary 1,000 turns, twice the number of the primary, or a ratio of 1 to 2, let's see what happens to the voltage. Presto, Mr. Volt became twice his size. The ratio is 1 to 2, so the voltage doubles. In this case, the voltage is stepped up because the secondary coil is the largest. If, on the other hand, the secondary is the smallest, the voltage is stepped down. Either way, however, voltage is transformed. Now, it's important to realize that a transformer doesn't add any energy to a circuit. It merely changes or transforms the energy that already exists in the circuit from one voltage level to another. The total amount of energy in the circuit must remain the same. Now, if it were possible to construct a perfect transformer, there would be no loss in power in the transformer. Power would be transferred from one voltage current level to another. Since power is the product of current times voltage, an increase in voltage by means of the transformer must result in a decrease in current. And likewise, a decrease in voltage by the transformer must result in an increase in current. Now, stating in another way, we can say that a transformer which increases the voltage by a given ratio will decrease the current by the same ratio, and vice versa. For example, if we apply 10 volts at 10 amperes, or a power of 100 watts, to the primary of a step-up transformer, which has a turns ratio of 1 to 10, the voltage in the secondary would be 10 times that of the primary, 100 volts. But the current in the secondary would be 1/10 that of the primary, 1 ampere. The power in the secondary, however, would still be 100 watts. Now, let's suppose the same 10 volts at 10 amperes was applied to the primary of a step-down transformer, one which has a turns ratio of 10 to 1. The power in the primary would again be 100 watts. The voltage induced in the secondary would now be 1/10 that in the primary, 1 volt. The current in the secondary would now be 10 times that in the primary, 100 amperes. The power in the secondary, however, remains at 100 watts. Now, thus far, you've seen that if the secondary of a transformer has more turns than the primary, the voltage is stepped up. Whereas if the secondary has fewer turns, the voltage is stepped down. Now, later you'll see transformers in which the primary and secondary have the same number of turns. Such a transformer has a turns ratio of 1 to 1. Unlike the step-up and step-down transformer, a 1 to 1 transformer neither increases nor decreases voltage. The voltage and current available at its secondary is the same value as that applied to its primary. Now, the transformers we've dealt with thus far were assumed to be ideal transformers. That is, they were considered to be 100% efficient. Such an assumption is quite all right from a theoretical viewpoint. However, from a practical viewpoint, the construction of an ideal transformer is an impossibility. The primary reason for this can be realized by discussing a factor known as the coefficient of coupling. The coefficient of coupling, which is represented by the letter K, is a measure of the degree of coupling between the primary and secondary coils of a transformer. The coefficient is obtained by dividing the number of magnetic lines cutting the secondary coil by the number of magnetic lines actually produced by the primary coil. For example, if the primary of this transformer produced 10,000 magnetic lines, but only 8,000 lines cut the secondary, then the coefficient of coupling would be equal to 0.8. Now, if all of the magnetic lines produced by the primary coil of a transformer were to cut the secondary coil, the coefficient of coupling then would be 1. The coefficient of coupling for an ideal transformer is also 1. However, even with high permeability iron cores, a few of the magnetic lines fail to cut the secondary and are, in effect, lost. Now, this prevents the coefficient of coupling from ever being exactly unity, or 1, in an ideal, or I should say in a practical transformer. It should be pointed out, however, that a coefficient of coupling of 0.98 is possible between the coils of a well-designed transformer. Now, in general, there are 4 types of transformers. They include power transformers, audio transformers, RF, radio frequency transformers, and finally, auto transformers. Power transformers are used to step up or step down AC voltages occurring at the power frequencies, which you'll recall include 50, 60, and 400 cycles per second. It should be pointed out, however, that a particular power transformer is designed to operate at only one of these frequencies. For example, a power transformer that's designed to operate at 60 cycles per second couldn't be operated at 50 and 400 cycles per second. Now, quite frequently, and especially when dealing with schematics, you'll have to recognize a type of transformer by its schematic symbol. The schematic symbol for the power transformer can usually be identified by there being more than one secondary winding. In this case, there are 2 secondaries. However, other power transformers may have a different number. You'll notice that each secondary has a different number of turns. One of the secondaries has fewer turns than the primary. Therefore, it produces less voltage than that applied to the primary. The other secondary, though, has more turns and thus produces more voltage. Now, you'll also notice that the power transformer is constructed with an iron core. Now, unlike a power transformer, which is designed to operate at a specific frequency, the audio transformer is designed to operate over the entire range of audio frequencies, which is generally considered to be from 20 to 20,000 cycles per second. The schematic symbol for the audio transformer resembles that of the power transformer. The audio transformer, however, usually has only one secondary winding. Like the power transformer, the audio transformer, too, is usually constructed with an iron core. Well, at frequencies above 20,000 cycles per second, the RF transformer comes into use. At these frequencies, hysteresis and eddy current losses in an iron core become so great they have to be prevented. Therefore, RF transformers generally have an air core. The schematic symbol for an RF transformer, then, is easily identified by there being no vertical lines between the primary and the secondary coils. Now, a special type of transformer which uses only one winding for both the primary and the secondary coils is the auto transformer. In addition, an auto transformer can be used either as a step-up or as a step-down transformer. When used as a step-up transformer, all of the primary winding is part of the secondary winding. Here you see that the winding has a total of 1,000 turns. 600 of these turns serve as the primary, while the entire 1,000 turns serve as the secondary. Now, when an auto transformer is used as a step-down transformer, all of the secondary winding is part of the primary winding. Here we see now that the entire 1,000 turns are serving as the primary, while only 600 are serving as the secondary. Now, auto transformers are sometimes constructed with a sliding contact, as we see here. When a control is varied on the transformer case, the secondary voltage can be varied from the maximum voltage induced in the winding down to 0 volts. As you can see, this type of transformer is called a variable auto transformer. However, it's probably most commonly known as a variac. Now, auto transformers are normally used in power circuits. However, they may be used for audio or RF use. That is, designed for audio or RF use. The symbol for an auto transformer used in a power or an audio circuit will indicate an iron core. The symbol for an auto transformer used in an RF circuit will be the same, except it will not indicate an iron core. Now, even though we showed you definite symbols for each of the types of transformers, you may find occasions when they'll differ. However, in these cases, you can readily tell the type of transformer simply by noticing where it's being used in the circuit. For example, if a power transformer is being used in a power supply, or if a transformer is being used in a power supply, then you can rest assured it's a power transformer. Now, earlier we showed you, or you learned, that the turns ratio of a transformer determines whether the voltage is stepped up or stepped down, and by what amount. There will be times when you're troubleshooting electronic equipment, however, that the turns ratio of a particular transformer won't be given. Thus, you'll have to determine whether the transformer is a step-up or step-down transformer by other means. Now, one way to readily determine this is simply by applying voltage to the primary winding and then measuring the output voltage of the secondary winding. Now, over here, I have a transformer demonstrator. As you can see, it's composed of an iron core and 2 windings. One of these windings will serve as the primary of the transformer, while the other winding will serve as the secondary. In the demonstration, we'll be using the bottom winding here as the primary. Now, here I have a power supply, and from these 2 terminals on the power supply, we can obtain 6.3 volts AC. I'm going to apply that 6.3 volts to the primary of this transformer, and then we'll use our PSM6 and measure the voltage available at the secondary. Let's go ahead then and apply the 6.3 volts to the primary of the transformer, which, as I've already mentioned, is the bottom winding here. Now, if we'll turn the power switch on, we have 6.3 volts applied to the primary of the transformer. Now, the PSM6 has already been set up to measure AC voltage on the 50-volt range. So, let's go ahead then and see how much voltage is available at the secondary. If we'll take a look at the AC scale now, and it'll be the middle row of numbers, you can see it indicates 11 volts are available at the secondary. Now, since this is greater than the 6.3 volts applied to the primary, this then readily tells us that this transformer is a step-up transformer. Now, if the transformer in question was a step-down transformer, then it's obvious that just the opposite would be true. The voltage measured across the secondary would be less than the voltage applied to the primary. Now, another way you can determine whether a transformer is a step-up or a step-down transformer is by means of resistance readings. Since a transformer winding is a continuous piece of wire, it should have a definite amount of resistance. And the more turns the winding has, the greater the resistance will be. Therefore, by comparing the resistance readings of the various windings, we can determine the turns ratio of the transformer, and thus whether the transformer is one which steps the voltage up or steps it down. Well, let's measure the resistance of the windings in our transformer we're using here and see if this holds true. Before we do it, however, there's a few words of caution I should point out, and that is, whenever making resistance checks in a transformer, ensure there is no voltage applied to the transformer. So let's turn the voltage off, disconnect the lead so we'll get accurate readings on our transformer windings, and let's proceed with the checks. Now first we'll have to set the PSM6 up so it'll read resistance. We'll place the function switch in the ohms position, and we'll place the range switch in the ohms times 1 position, since we're dealing with a relatively small amount of resistance here. And now, so we'll get an accurate reading, let's zero the meter. Well, we can see it was already zeroed. So let's go ahead now and measure the resistance of the primary winding. All right, if we'll take a look at the meter now, we'll see that the primary winding has about 10 ohms of resistance. All right, let's go on over to the secondary winding and see how much resistance it has. Remember now, we're on the ohms times 1 scale, and this time we can see the PSM6 indicates about 20 ohms of resistance for the secondary. Now this indicates then that there's twice as many turns in the secondary as there is in the primary. So the turns ratio is 1 to 2. Thus the transformer is indeed a step-up transformer. And a step-up transformer then, the resistance of the secondary is higher than the resistance of the primary. So for a step-down transformer, just the opposite would be true. The resistance of the primary is higher than the resistance of the secondary. Now, 2 other checks you'll have to perform on transformers quite frequently are those for an open or a shorted winding. Both of these checks can be performed with an ohm meter. Over here I have 2 windings identical to the windings we're using in our transformer. One of these windings has 150 turns. Its normal resistance is 10 ohms. This winding has 300 turns. Its normal resistance is 20 ohms. The big difference in these 2 windings, however, is that one of them is shorted and one of them is open. So let's use our ohm meter and see if we can tell which is which. Now remember, the PSM6 has already been set up to read resistance on the ohms times 1 scale. So let's go ahead and check the resistance of the 150 turn winding first. If we'll take a look at the meter now, we'll see that it reads infinity. Well, since the PSM6 always reads infinity for an open, this then indicates that the 150 turns winding, the one I'm now measuring, must be the open winding. We see then that an open transformer winding, primary or secondary, is indicated by a reading of infinity on an ohm meter. Now that brings us to the 300 turns windings. And since the 150 turns winding was open, then the 300 turns winding must be shorted. But let's go ahead and check it and see what indication we get. We'll take a look at the meter now. We'll see that the resistance of this winding is only 12 ohms. But we've already pointed out the normal resistance of the 300 turns winding is 20 ohms. Thus, we can conclude that some of the windings or turns of this 300 turns winding must be shorted. Well, as a matter of fact, I've already figured it out, and approximately 70 turns of this 300 turn winding are indeed shorted. Well, we see then that for a shorted transformer winding, the ohm meter will indicate a resistance less than the normal resistance of the winding. Now, of course, the greater the number of turns shorted, the greater the decrease in the resistance of the winding. Now, it's also possible for one of the transformer windings to be shorted to the core of the transformer, or even for the different windings to be shorted together. However, these troubles can easily be located since the resistance between any two windings or between any winding and the core should always be infinite. Well, that brings to a conclusion this lesson on transformers. Later, when you study the various types of electronic circuits, you'll find the transformer's applications to be both varied and many. So learn them well, and until I see you again, goodbye.